Now, welcome back. We start to solve the problem. This is a design problem suitable for your practice because you are engineer. What is the practice we need to do? Because you see, we should to determine the required cross-section area of bar. We need to determine the required cross-section area of bar. That is the minimum area. And also the required diameter of the pin as a support C. The idea is if you do not have enough area here, it will collapse. So this is a typical design problem for you here. Now, going to solve. Okay, when we solve the problem, before the previous semester, you already learned like mechanics of engineering. I think most of you already learn mechanics of engineering, and in last previous course. I think everybody already learned mechanics of engineering. So here, I don't want to repeat more because we don't have enough time to repeat the mechanics of engineering. Maybe physics you already learned before. I directly give you the answer. The reaction at A equal to, I directly give you the answer 5.5. kilonewton. Calculate at practice time. I ask you calculate because this is your previous course. I don't want to calculate here. And also the reaction at C points is equal to 5.152 kilonewton. Also, you need to calculate at practice time. This is your previous course. I don't want to calculate again. So now, following, so I will teach you. It's about the design. Because you know, all of this is an equilibrium equation. You already learned very well before. But now, from this semester, we start to learn constitutive equation. second is a material property. And the third is material strength. This is a new you learn in mechanics of material. So now we are talking about the design, the different from the different from your previous learning. And first, we will calculate the minima area of AB. That means here we will calculate the area here. So first of all, you will know the force and at AB bar is just equal to reaction of A. Force on A, so that means equal to 5.6 kilonewton. We say this is a force. So in this case, we need to calculate the minima area. You mean minima area is equal to, according to our discussed before, this is a force at the bar, and divided by we call allowable stress. Allowable. Because according to the equilibrium equation, force divided by stress is equal to the area. So we can directly 5.16 divided by, and the allowable stress it already give us is 125 megapascal. From the practice, this is they already give us the allowable stress. That's why we can get the area is 44.1 millimeter. So that is the minima area here. From here, we may go back to the it already give us the allowable stress 125, and the allowable shear stress, allowable stress here, allowable shear stress here, allowable shear stress here. Yeah, so allowable tensile stress here, allowable shear stress here, because there is an interface. So we need to calculate the shear stress here of the bolt. Go back here. Okay. This is the first answer we already get. Now we will calculate another. We will consider here consider here should be careful about this. This C is a bolt C here, and it's subject by a. You look this reaction C here. Is a the reaction C here on the bolt. On the bolt here. So should the reaction C should equal to the shear on the bolt. The shear on the bolt. Shear force on the bolt. So that means when you calculate the minima area, that means the minima area is equal to shear stress divided by 2 allowable shear stress. And you will say why we put 2 here. The 2 means it's a two-phase. Two-phase. This side and another side. This side and another side. So you need to divide it by 2 more. So the answer should be you get is you can write down is 5.152 and divided by 2 multiplied allowable stress we already give you is 45. So the answer should be 57.2 meters squared. So this is the minima area, and the minima diameter is equal to square of 4 A minima and divided by pi. Equal to 8.54 millimeter. So we can get the minima. Now we can get so we can get the solution. We can get us a solution of minima diameter of ball. Okay, we finish.